Hi guys, some of you in the last video asked if I could perform the simulation with the flyback converter with the TL431. Now, before doing that, I think that the best approach is first to study what a TL431 is, and then to use it implemented as a Type 2 compensator. So first of all, the TL431 is a adjustable shunt regulator, which has a fixed reference voltage of 2.5 volts. Now, the first thing that we're gonna see is the feature of this one in the datasheet. So first, the reference voltage tolerance at 25 volts. Every voltage reference must be stable in temperature. So this is the first thing that we're gonna see. Second, you have to see the drift and also the absolute maximum ratings in order to make it work. So the adjustable output voltage is from Vref to 36 volts. So the first thing that we're gonna notice is that if you employ this in a DC-DC converter, your output voltage cannot be under Vref. Okay, so the minimum output voltage will be the voltage reference. Then we have the typical temperature drift, but this has to be analyzed in a specific characteristics. Then we have low output noise, and the typical current involved, the typical impedance involved is very low. This is good, okay? Then we have the sync current capability, 1 mA to 100 mA. It means that in order to make it work, we need at least to bias the circuit with 1 mA. The second part of the datasheet tells us how it can be employed, the typical application, and some description. The output voltage can be set to any value between Vref and 36 volt, with two external resistor. Meaning that if this is the circuit and this is the voltage reference, we expect the equation to be something like that. This is the cathode, this is the anode, and this is the reference voltage. Let's see why it lags so much, guys. So anyway, what is this? What is this paint, guys? I switched to Windows 11 recently, but what is this? Seriously. Okay, so this is the input, and this is the reference voltage. Now, if I apply a divider here to the output voltage, R1, R2, since the output impedance wins on the output, you don't have VO equal Vref, but rather the contrary, times the divider, okay? But rather the contrary. So it is Vref which is equal to VO times the divider. And so, if you follow this equation instead, you will discover that VO is equal to Vref times, let me write it down here, VO times Vref times R1 plus R2 over R2, okay? And so VO is equal to Vref times 1 plus R1 over R2. This is that's why, because the reason is because the output impedance wins on the output, and since the reference voltage is fixed, you have the output voltage which follows this equation instead. So it's not like you are imposing the reference on the outside, but rather that the reference is fixed and the output voltage is decided on the true resistor. And this equation is confirmed also in the application notes here. Like you see here, you put two resistors here in the reference, and then you decide the output voltage with this equation here. So the first thing that we're gonna see is this circuit here on LTSPICE. Naturally, the first thing that you're gonna do is to import the TL41, and with the right click here, you create the symbol. If you have some creativity, you can do something like this, but it's not mandatory. So I prepared already the circuit for you, and if you understood what this circuit does, then you expect the output voltage to be exactly as the equation. So let's put the equation written here. This is the reference voltage. Let's call it ref. Okay, this is the reference voltage. Let me check. Okay, and we said that the output voltage is equal to the reference voltage. So V ref times 1 plus R1 over R2. Now, if we make the parameter .param R1 equal to 3 kilo and .param R2 equal to 9 kilo, then, according to my calculation, you should have basically 3.3 volts, because you have 1 plus 1 over 3, and we have 3.3 volts. Now we can put this resistor here R1, and the other resistor R2 here. And if you run the simulation, we should see... I'm sorry. I put this was my mistake. Let's call this this node reference. Okay. Just my little mistake. Okay. Ignore that simulation. Another kind of simulation is running right now, but let's ignore that. So let's ignore that simulation right now. Okay, so we have this kind of okay. This is the comment. Okay. Okay, so according to my calculation, we have 3.3 volts, and the real output is more or less what we expect. Yes, exactly what we expect. Naturally, if I increase the output, if I increase the load, this voltage starts to diminish. If I put 10, then it starts to drop, and if I put 1, at a certain point, it will start to drop, because the efficiency is not so the efficiency is not so good as a power supply. So but by the way, you won't use this circuit as a power supply, but rather as a reference. The datasheet though suggests also an application in which you can use this circuit as a 5 volts reference, and you can understand immediately why you have 5 volts here, because you have the same resistor divider, and so since it is the same, you have 1 plus the same ratio, so R over R, which is 1, so you have basically 2, and so you have VO equal to 2 times Vref, so you have 5. Naturally, the more current you drain, the more drop you are gonna have in this transistor, because this is the VCA, and this is in saturation region, and so you're gonna have a very high voltage drop. Let's simulate this circuit on LTSPICE as well. And of course, I have already prepared for you. As you can see, you have the TL431, the divider here, 2.5, and the output voltage, 5 volts. Now you do have to provide 1 milliamp here, or at least 10 milliamps, to bias this guy. The reason you want to do that is because basically, inside this guy, there are a lot of op-amps. Sorry, there are a lot of transistors, which you have to bias, basically. The equivalent schematic is basically an op-amp. In the minus you put the V reference, and in the output you put a transistor here with the diode. Okay, it's something very similar to this. I can open the circuit. Yeah, so as you can see, the reference, the Vref on the minus, the reference on the plus, and then basically you have the transistor outside with the diode. And this and this is the cathode, and this is the anode. Okay. let's simulate also the circuit here. And as you can see, I have 5 volts and a current of 300 milliamps. Now, you do not want to use this circuit as a power supply. The reason is it's not a good, it's not a DC converter. So LDOs, generally speaking, have 50%, 60%, 70% of efficiency, but no more than that, okay? Now, the higher the drop voltage, the less the efficiency will be. So I already prepared the text for the efficiency right there, but if you plug this into here, so add traces, you add this, you're gonna find out that the efficiency is 50%. If I reduce the VCA voltage, so let's put 7 here, the efficiency should increase, but not so much. If I put 6, if I decrease the load, yes, 82%. So meaning that you can drain like 10 milliamps from this circuit, okay, but no more than that. What you can do is also to make, you can make something interesting. You can make a sweep of efficiency in LTSPICE and doing something like this. As you can see, I prepared for you also an efficiency curve. You can plot the efficiency with the time, sorry, not with the time, but with the current on the side here. And you can plot the efficiency here. As you can see, you're gonna have with the voltage of input voltage of 9 volts. Okay, so the VCE drop is equal to 5 volts. Sorry, 4 volts. As you can see, you have this is 30% and this is 50%. As you can see, you have a plot like this. And if you drain basically more than 300 milliamps, the efficiency is gonna drop very, very fast. Okay, so this is not for supplying power supplies. Okay, it's not for supplying something very big, but just 10 milliamps. Okay, no more than that. Unless you design more complex circuit, but in that case, I would rather buy an already handmade, an already commercial made LDO, and that's it. Okay, a commercial made LDO can even have 80% of efficiency, so there is no reason to do something like this on your own. Okay, if not because you're a hobbyist, and then okay. So this is one of, so you can find in the datasheet more and more application of this guy, but honestly, in power electronics, what do you use these guys for? Basically, as a Type 2 compensator. Okay. Yes, there is the precision high current side regulator, current sink, current there, precision 5 volts, PWM, blah 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 blah. But at the end of the day, in power electronics, use this guy as a voltage reference and then as a PI2 compensator. So I think that we can close this guy. We can close this shit and close it, and then we can open the already prepared closed loop back. So this is a closed loop back, and because before doing the TL, I explained very quickly the prototype that I prepared for you. This is a buck converter, the classical buck converter, with a switching frequency of 250 kHz, an input voltage of 10 and an output voltage of 5. Okay, very, very, very classical exercise of power electronics. This is a Type 2 compensator. It is wrong because you would need a Type 3 compensator, but I don't care because it does quite well the job. So you stimulate as any control system theory, you stimulate the circuit with a step load and you see how it reacts. Okay, as any control engineer would do. So you check the output, and as you can see, you have the drop voltage. Then what the circuit does is to adjust the duty cycle here to provide more energy to the inductor, and of course to have more energy on the output to recover as fast as possible from the request, from the load request. Naturally, if you change this resistor here to 1K, you're gonna have less gain, and so the drop will be much more than you're gonna see before. And as you can see, the drop has increased a lot. The drop stands to even to 2 volts, so the drop is very, very high because it doesn't have much gain to recover very quickly. So you should put a much higher resistor. Naturally, this resistor have to be designed based on your system, but by the way, this as a prototype does quite good the job. Our purpose here is not to design the compensator for now. I have already explained how to design this compensator in another video, but anyway, I can pass this, I can upload this as well. Now, what we want to do is to check if this guy behaves like a Type 2 controller. I put it here the Type 2 controller which I put on the circuit, and I put also the Type 2 here of the TL431. As you can see, it behaves like a Type 2 controller because if you remember, just let me give a little bit reminder. This is the RC, which basically decide this pole here, and then there is the little capacitor here, which decides the pole at a higher frequency. This is useful to cut frequency noise, and this is useful to compensate the inductance given by the LC. Okay, sorry, the pole given by the double pole given by the LC. So the transfer function of the buck converter, as you remember, is let me draw it right here, is something like this. Okay, you need to compensate the pole here. Okay, and so the 1 over 2 pi LC, and this one compensates the ESR of the output capacitor, which is 1 over 2R ESR. Okay, so basically this is the story. You have to compensate then the pole given by the inductance and the output capacitor. Okay, let's implement this guy on our circuit, and let's compare the everything. Okay, so let's open. I already did this. Let's open this. As you can see, the circuit has not changed much because you have always 5K, the TL431. On the cathode you have 1K, because if you remember the previous circuit, you have to bias always the cathode with 1 milli, or at least with something below 100 milliamps. And then you have the compensator put on the ground. So the cathode output goes to inside the triangular waveform. This is compensated. This is compared with the triangular waveform, and then this is given to the gain, which thanks to the class B amplifier, it provides the PWM for the MOSFETs. Let's run the simulation. Again, we have the load, the step load, and we have the output voltage. So the first thing that we see, yes, let's close this. Okay, the first thing that we see is that first, since this is an ideal op-amp, logically speaking, it's way more cleaner than the TL. But because it is a universal op-amp, and of course it's an ideal component. This is a real component instead, and of course it has way more oscillation. But despite having so, the output voltage here has less drop than the output voltage of the op-amp. Here I have 3.2. Let's mark it there. Okay, 3.17, and let's move it here. Instead, here I have 3.37. The meaning of this is that from what I this is not a bug. This is just me, which I'm really terrible in drawing. Okay, but it is connected. Okay, it is me that I didn't close the rectangle properly. Okay, my bad. But anyway, this means that the TL431 is faster than this in recovering, of course, from the from the drop voltage. But as you can see, there is way more noise. You can understand this by, as you can see here, zoom it here, zoom it there. We have more ripple on the left side than in the right side. So the answer is, can we use the TL431 in the flyback converter as a compensator? Yes, of course. The architecture has equations already done in literature. Okay, so you can use that, and you can also use as a non-isolator by a PI2 compensator, type 2 compensator, also in buck converters. The only problem is that if you want to go below 2.5 volts, you won't be able to do that. Because in the datasheet, it's written clearly that the minimum voltage is Vref. Okay. Now let's play with these two circuits. Okay. Let's put here 10 kiloohms, and let's put here 10 kiloohms. And let's run both simulations. This goes to 3.6. So I'm changing the voltage, I'm changing the divider, and I change the voltage. Let's run also this. And this goes to 3.87. Well, I still have some ripple, but I think that this ripple here can be improved by increasing the output capacitance, because this ripple is given by the switching frequency. So, yes, it's given by the switching frequency. No, it's not given by the switching frequency. This ripple here is not given by the switching frequency. Ho. This is not beautiful. 150 kilohertz, this is a bit of instability. But, so if I run the simulation again, I don't think that I'm gonna solve this problem. And as you can see, I didn't solve it, because it's not given by the switching frequency, rather by loop problems. But I'm still quite satisfied from the circuit. So we explored this different kind of application. We explored the shunt regulator schematic and the voltage regulator, and we explored also the solution which we do use the TL431 as a compensator. Well, what can I say, guys? Thank you for watching this video, and I hope that next time I can bring you the flyback converter with the TL431. See you in the next video. Thanks.